see, 5 won't go into 2, will it? No. But 5 goes into 25 5 times, you see?
You're wrong, Billy. Now, I'm a pretty good mathematician.
Percentage. I figure 75% to you, Panma, and 25% divided between the 5 of us. Yida, Crowbar, myself, Tom, and the baby. That makes 5% for each one of us.
Billy, you're cheating yourself. If there's 25% divided among the 5 of you, that's 14% apiece.
Oh, no, listen, Pa. I wouldn't cheat you. You know I wouldn't. Now, look here. I'll show you. Let me rub this out here. And now, 25 divided by 5 is 5. You see, 5 won't go into 2, will it? No. But 5 goes into 25 5 times, you see?
No, you're wrong, Billy. Now, I'm a pretty good mathematician. Now, 5 into 25, 5 won't go into 2, will it?
No.
But 5 goes into 5 once. Now, we didn't use the 2 before, so we'll bring it down here. Now, 5 into 20 goes 4 times. There you are. 5 into 25, 14.
And then they go on. I think it's worth revisiting because maybe you feel a little bit like there's some kettle math going on in your head or something. So keep working at it. Practice will resolve it. We have the practice session, the recitation session tomorrow night. We're going to work on gradient, divergence, and curl. And I'll have different levels of problems. I'll have some easy problems, some intermediate problems, and I'll have some challenging problems. So I think even if you feel like you've got it down, I'll give you some a little bit harder stuff you can work on. Not more difficult in terms of just more complicated functions, but more subtle in some sense that require you to think some more. So even if you've got the calculational part down, I'm going to give you something that'll make you go, huh, when you're done. Okay, so there'll be plenty of stuff for everybody to work on. And good opportunity to just practice stuff. So we're continuing the discussion about magnetostatics. And in particular, I want to continue the discussion about the Helmholtz theorem. The Helmholtz theorem talks about vector fields in general. And it says, in general, a vector field can be decomposed. And by a vector field here, I'm going to really, it has to be, there's some restrictions on this. It has to be not a pathological function, not some bizarre function that you might, but things that you expect to see in physics. And physicists can get away with this kind of stuff, really, because we're used to dealing with functions that behave according to how things behave in the real world. So generally, they're not crazy functions. So mathematicians may get a little upset with us because we're implicitly restricting our discussions to things that aren't really bizarre. So by vector field here, I mean something that is well behaved, it's differentiable, continuous. Okay, so a vector field can be decomposed into 2 parts. Now, when I say decomposed, I don't mean physically decomposed. For example, if we're talking about a vector field like a current density, I don't mean it's physically decomposed into 2 parts. What I mean is it can be thought of in the mind and mathematically as being a superposition of two pieces. And so let's start here. I'm going. Maybe I should just start with a generic field first. We'll just have some field W. I can break it into 2 parts, which are going to be given subscript C and D. So the C part has no divergence, and the D part has no curl. Sounds like a nursery rhyme or something. One part has no divergence, the other part has no curl. Sounds like I'm going to go somewhere with this. Okay, so in other words, it has no divergence. So this part is 0. The divergence of WC is 0, and the curl of WD is 0. Okay, now that part that has no divergence, it might have a curl. It might. But you know for sure it has no divergence. And so it's called WC, not because it definitely has a curl, but because it can have a curl. And the WD is labeled D for divergence, not because it has a divergence, but because it has no curl and it may have a divergence. Okay, that's the subtlety here. WC here, you might want to call it the curling part, and that would be okay, but it doesn't mean that it definitely curls, it just can have a curl. And the WD can have a divergence, not that it does have a divergence. It seems a little subtle here, but let's go, that's the content of the Helmholtz theorem. Now it's written down mathematically in a different way in the book, but he discusses it this way. So let's take an example. Let's go back to electrostatics. The electric field, let's suppose we look at an electric field. Going back to electrostatics, let's consider what the Helmholtz theorem, the consequence of this for electrostatics. That I can decompose an electric field into a part that has no divergence and a part that has no curl. Now let's remember Maxwell's third equation. What is Maxwell's third equation in the electrostatic condition? Ms. Myers, go ahead.
The curl of 0.
Yeah, she's air writing this, so I know she knows the answer here. Curl of E is 0. Right? So now I just said that, so this is going to be, and the curl of sum is the sum of the curls. Okay? And by definition, E sub D is 0. The curl of E sub D is 0. That's the definition of that part. So we're left here saying the curl of this remaining part is 0, so we can get to the conclusion finally that E sub C is 0. There is no part of E that curls, right? So E sub Z is 0, so you're left only with an E sub D. Now what is the first Maxwell's equation? We had the curl. Now what's the divergence of E?
Divergence of E is equal to 4 pi charge density.
4 pi times the charge density. Now we've determined that E sub C is 0, so all that's left is this E sub D part. And that part is what is related to the rho. Okay? Simple enough, but we'll hang on to this because we're going to keep using this. Now let's determine for the magnetic field. Let's determine this for the magnetic field. Let's look at, in the magnetostatics case, we now have two equations known as Maxwell's second and fourth, but in the magnetostatic condition. What are Maxwell's equations, second and fourth equations? It's going to be the divergence and curl of the magnetic field. God bless. So let's start with the divergence of the magnetic field. What is the divergence of B? Always 0. Okay, and we said that that the B sub C is the part that never diverges. This is always 0. Divergence of B sub C. So it tells us that B sub D is 0. That there is no diverging part of the magnetic field. Right. Okay, that seems kind of obvious. Okay, it may seem like we're, why are we doing it this way? We kind of had this feeling, but the power behind this is going to come. Okay. Now let's look at the curl of B. What is the curl of B?
4 pi J over C.
Very good. Mr. Hetherington remembers 4 pi J over C in the CGS system. So just as the divergence of E diverges out of a charge density, B curls out of a current density. Okay, now let's look at this, the curl of B sub C and the curl of B sub D. Well, we said that B sub D by definition has no curl. That's what we mean by B sub D. So the curling part of B is what comes from J. Okay, seems like, what have we done here? Well, there is a point to this. Hang on here, I'll show you. Okay, now the other way of writing Helmholtz theorem is that I can take any field and write it as in two forms, two parts. A part which is the curl of some other vector field A and the gradient of some scalar field beta. So I can associate with any vector field W a vector field alpha and a scalar field beta. And these are called potentials. Alpha and beta are potentials for W. Now, potentials here, what we mean mathematically, we've taken the idea of a potential energy and generalized it mathematically. They're called potentials by analogy to potential energy. Mathematically, they're just functions, but we're extending this, as we often do, extending physical concepts into mathematics, right? I mean, that's what mathematics, we extend quantity, and we study just quantity per se. Okay, so alpha and beta are called potentials, mathematically potentials. So any vector field can be associated with a vector scalar field in this fashion. So we could do that with the electric field. So we could have an electric potential, and we could have both the scalar and vector potentials for the electric field. But notice that we said that first part has to be 0. There. If you look up what we did there, that first part has to be 0. We're left only with this. And remember here, what we said was that E is the negative gradient of phi. So in fact, what we were doing was a special case of the Helmholtz theorem when we wrote the electric field in terms of a scalar potential. So there is no vector potential associated with E. It's just a scalar potential.
Where does the negative come from?
Yeah, that's just by convention we choose a negative sign for the electrostatic potential. And that's because the reason for that sign is because if you go back to the relationship between the potential energy and the force is the negative gradient of the potential energy. The force is downhill. It wants to go lower in energy, so that's the reason for the negative sign. Positive charges will move in the direction of the electric field, but downhill in terms of electrostatic potential. Okay, now the magnetic field is the other way around. We could start with we have possibly a scalar and vector potentials for the magnetic field, but we just went through the argument, so this term is 0. And so this is going to be what we will call the vector potential A. So again, we have this funny thing here where we've got the scalar potential for E and the vector potential for A is a reflection of the understanding of the Helmholtz theorem and also the basic equations that we have. In this case, for the electric field, the curl of E is always 0 in the electrostatic condition, and the divergence of B is always 0. Okay, so now you're going to do some homework here next for Friday. Let's go back to this condition here. I want to check something here. Let's suppose that we haven't decided yet that this alpha must be 0, alpha E must be 0. Let's go back to this. Now, so you're going to get here the divergence of the curl of alpha. And this is the divergence of the gradient of beta. Okay? You'll show in your homework that this is identically 0 for any alpha. The divergence of the curl is always 0. You're going to demonstrate that in your homework. Okay. That if you have a field that comes about from a curl of another field, that it cannot diverge. If it's the curl of some field, the best it can do is curl. It can't diverge. So the curl of a field is itself can only curl. Okay, and you'll demonstrate that in homework. And likewise, if we take the curl of B here, and we look at the curl, then we get the curl of alpha M, and we get the curl of the gradient of beta sub M. You're going to demonstrate in your homework. Oops, that's a curl. Excuse me. This is a curl of a gradient. You're going to demonstrate in your homework that the curl of a gradient is always 0 for any beta. Okay, so that's how it all fits together. All these pieces here. Okay, so the bottom line is this. After you go through all those pieces, you'll see that the bottom line is this. In the electrostatic condition, the third equation, Maxwell's third equation, means that E can be written as the gradient of a scalar. And we determine that the electrostatic potential is a further specification of the electric field. So it's a condition of the plana. It's a measure of the state of the plana, both E and phi. Okay. And whereas by contrast, in the magnetostatic condition, we have the kind of the complement. Instead of having something that has a divergence, we have something that has a curl, and that means that B can be written as the curl of a vector potential, and that there's no scalar potential for the magnetic field. There's nothing like phi for the magnetic field, and that's a condition of that. Okay, so the Helmholtz theorem is trying to help you see that this is quite general. It's not special here to electric and magnetic fields, except that physically there is such a thing as A and phi. So what is A? We said phi is to E as A is to B, except that phi is a scalar and A is a vector. So what in the world is this A? We said phi, we have a kind of a physical feeling force related to a potential energy. If we have the plana has an E field and a phi, and we put a charge in there, then the force will be QE, and the potential energy will be Q phi. Right? So we have an electric field and a phi present, and we put a test charge Q in there, in this. Then we get a force on that test charge, which is QE, and the potential energy will be Q phi. So you can think of the electric field as the force per unit charge on a test charge. Or the electrostatic potential is the potential energy per unit charge of a test charge. So you could think of it that way. You could measure those things that way. If you put a test charge in there, measure the force, then you can back out what the electric field had to be before you put the charge in. And if you put in the test charge, you can measure its potential energy, and you can back out what the electrostatic potential was there. Okay, now let's do the same thing. Let's put a test charge. I keep missing the point there. Okay. Let's put a test charge. We have some plana which has both B and A, and this is trying to sort out here what A is. Okay. We put a test charge Q, but if we put a test charge in, what's the force? Well, it depends on the velocity, which is, of course, a sign of the impetus that's present in the body. So the force is zero if it's not moving, but if it's got impetus, and from the motion is a sign of its impetus. So if it's got impetus, it's moving, therefore it will have a force on it. Okay. All right, but what is this A? QA. What does QA mean? What is that? Yeah, well, Mr. Miller's been in my office, so he just volunteered to answer here. So, but I'll give you a brief answer here. So here, this is a potential energy, right? Q phi is a potential energy, or in other words, phi is a potential energy per unit charge. It's a potential energy per charge for a test charge that we put in there. And the answer for for A is going to be QA is a potential momentum. And you're not going to be able to understand yet when we come to chapter 4, right at the beginning. I promise you'll understand A much better. It's related to magnetic induction. What I mean is revealing the physical significance of A. That revelation will come to you when we study magnetic induction. Magnetostatics, because we're keeping the wires fixed, they can't move, and you can't change the current in the wires, so there's no magnetic induction. So you can't see what is the physical significance of A until we start moving wires around and we start changing the current in the wires. And then we get induction going on, and then you'll see what A is. So I can't answer that question for you fully yet until we start moving things, and that's going to come in the next chapter. Okay, so but A has a physical significance, just as phi does. Okay. Okay, now we also noted from in the electrostatic case that we have this divergence of E, so we have both the curl of E is 0 and the divergence of E is 4 pi rho. So we were able to write, and also phi, if we put phi here, we get Laplacian. If we put E as the negative grad, that comes phi, so the Laplacian of phi is negative 4 pi rho. That comes from substituting in that E is negative grad phi and put that into the first equation. Okay, and that thing is the divergence of the gradient is called the Laplacian, and that's this. We studied that very briefly. Okay, just to complete these equations. So we showed in the second chapter, we examined that there was a way to get E and phi directly from rho. And that was, remember, E at some location and phi at some location. I'm going to write phi first. Whatever that charge density is, I can integrate over the volume, and I do this integral, and you can find phi. Now, you did this for a line charge in your homework. And we also did this example. We did the electric field. If I have the charge, I can find, remember that script R is R minus R prime. And we did that also for the electric field around a line charge. A little bit harder integral to do, but that was in there. Okay, so that's it. How does rho contribute to the electric field? Well, each little piece contributes 1 over distance squared in proportion to the charge that's present and pointed outward. And the phi is just that little charge divided by the distance, and then add it all up. So it's just a superposition principle. So I'm going to write the same thing now, the corresponding thing for the magnetic field. The divergence of the magnetic field is 0, and the curl of the magnetic field is 4 pi over Cj. Okay, and so I'm going to write this first for B. I can invert this. I can find the magnetic field from this, which is going to be 1 over C J cross R over R cubed dV prime. So it's kind of like the electric field, except it involves a cross product. And oops, this should be of R, excuse me, I need to tidy this up a little bit. J of R prime, there we go. Okay, pretty complicated integral, but in principle you can write it down. And this is a volume integral. Tidy this up a little bit more. You can do this on your paper, can't you? After you've written it down, you can just do that. Okay. There we go. So that, compare that to the previous page here. The electric field is rho times R over R cubed. So there's a similar expression for the magnetic field. You're not going to actually try to do that integral. It's pretty complicated, a little complicated. And also remember that A is, the curl of A is B, and so we can write down, there is an expression for A, too, directly from the current. I want to make sure I get this, oh yeah, I know what it is. I don't need to look it up. Very simple, pretty simple. So let's go back to look at the expression for phi over here. Here's phi. This is the charge that's present at R prime. Then you just divide by the distance, and then just add them all up. Well, there's the similar thing for A. J times dV prime, that's the amount of current that's present at that volume, has a direction, and then you just divide by the distance. So every little piece of current contributes to A, just one along the direction of the current, and then falls off like 1 over the distance from the source. So A fields are really easy to draw. B fields are harder for me to draw. A fields are really easy to draw. Let's start by doing just a current carrying wire like this. Let's suppose we have current carrying a wire like that. I want to sketch A around this wire. Okay, A goes in the same direction as the current. So you know it's going to be pointing up, and it's going to fall off like, it's just like phi. Now we did phi for a line charge. How does phi drop off from a line charge? Do you remember? No, that's the E field. Yeah, logarithmically. The E field drops off like 1 over distance, so phi goes logarithmic. So A is going to drop off logarithmically away from this. So A is going to be in this direction. It's going to diminish logarithmically, which means pretty slow. Logarithmic is pretty slow decay drop off, and it's going to look like this. Okay? So that's A, around the line. Okay, now let's put a curl meter into this thing. If I put a curl meter right here, which way will it spin? Clockwise. Which way is the magnetic field? Remember, the magnetic field is the curl of A. So which way is the magnetic field going to be? Yeah, into the board, right? Remember the curl meter, the axle of the curl meter is the direction, so the magnetic field is into the board. So I'm going to draw the magnetic field here as tail feathers. It's into the board, into the plane of the figure. If I put a curl meter on the left-hand side, which way is it going to go? It's coming out now, so the magnetic field comes out, right? B is the curl of A. So now you can see the magnetic field goes around the wire, right? Can everybody see that? How the magnetic field, if I look down on top of this, here's the current, here's the wire. Now the magnetic field is going to go this way. Okay, now don't be confused by thinking that you might be inclined to be confused that the magnetic field is somehow flowing that way around the wire. It doesn't. It doesn't flow like that. The propagation is outward from the wire again. If I turn off the current, this magnetic field goes away. So if I turn off the current, then let's look at the picture for A field. If I turn this off, that means that some region around the wire is going to go to 0. The A field is going to go to 0. So in other words, if I turn off the current in the wire, now it's 0. Now that means it's propagating outward. That means there's going to be a region over here. These guys have not gotten the news yet, not gotten the word that the current is turned off in the wire. Okay, but the parts of the planet that are close have gotten the message that there's no current in the wire. So the A field inside of this region is 0, and there's some distance here, which is c times the time, the speed of light times the time since you turned off the wire. So there's going to be a null region around the wire, and that's propagating outward. Now, notice that the propagation is perpendicular to the direction. The vectors are this way, but the propagation is this way. Okay, a similar thing happens to the magnetic field then. Here's the wire, and if I turn off the current in that wire, so I should draw the magnetic field. The magnetic field is going like 1 over the distance from the wire. Okay, now I turn it off. There's going to be a null zone in here. The distance, the radius of which is the distance that the light can travel in that time since I turned off the current. And then I get the magnetic field outside of that, right? So the news takes time to propagate. That's not magnetostatics. We're not able to really treat this situation yet. I just want you to get an understanding that the direction of these fields is not necessarily in the direction of propagation. In fact, the field vectors often point perpendicular or at some other angle to the propagation. So don't be a little confused here. You might see this magnetic field flowing around the wire. You might think somehow the magnetic field is kind of churning like that. It doesn't work like that. That's not what it means. Okay. Okay. So Okay, so we're sketching A-fields. Let's continue to sketch some more A-fields. A-fields are fun. A lot easier than B-fields to make. Let's make a loop. Let's make a loop like this, and I have current flowing in that loop. And I want to sketch the A field in the plane of this loop. You might think, well, I don't know exactly how it falls off with distance, but you know it's falling off with distance from the wire. So, what do you think? How is the A field going to look? And from that, we'll get B.
There's nothing inside the circle.
Yeah, there might be nothing, but there is something, actually. There is an A field. Good try. Sometimes there's nothing inside, so it's worth a guess. There have been situations where we find no field inside of things like that. Okay, but inside, if I'm at this point right here, just close to the wire, the part of the wire that's closest to it, now this is just a circular loop, right? It's not a sphere or anything, not a cylinder. It's just a wire loop. So the part of the wire that's close to it is going to have a strong effect, and the part farther away is going to have a weaker effect. So the net effect is to have an A field in this direction. But then as I get closer to the center, the A field is getting weaker. And right in the center, there's no A field. Right in the middle. So the A field looks like this. And remember, vectors don't curve. There's no arcs on this thing. Okay. And then it gets weaker as it gets closer here to the center. A little hard to draw. I started off with a little too small, but you get the idea. Okay, and here it's going. In what direction is the magnetic field? Yes, coming out of the board. Yeah, it's the curl, right? Where you put a curl meter in here, it's going to spin. It's going to spin in the counterclockwise direction, so the magnetic field is coming out. So I'm going to write in here B. And it's not uniform. It's not going to be uniform in this case. Not for a simple wire. Mr. Dowdle.
So we can like treat any like section of that loop as like a line, right?
Yeah, that's right. Any section of that loop generates a magnetic field. Now, implicit in this, we have to have a completely closed loop, right? So everything that I've done here has that assumption, and you can't have a piece of wire with current flowing in it, but then just ends dangling out there. And the reason is because you'll have current, you have charge building up on the ends, and we've neglected all of that. We're doing that to happen in the magnetostatic condition. You must have current flowing in loops. But if they flow in loops, then you can consider, I can construct the A field just by looking at the contribution that each part of the loop makes here. So outside, what is the A field going to look like outside? It's very similar. Yeah, it's going to fall off. I'm not sure exactly how it's going to fall off, but it's going to definitely fall off, and it's going to be in the direction of whatever part of the loop is closest to it, right? Okay, and which way is the magnetic field going? Into the board now. Magnetic field is this way. A field is so much easier than B field, and in fact we'll find a lot of reasons to use phi and A instead of E and B. And that's something that is not taught much. Use of phi and A. So you can sketch an A field, you can figure out the B field, and there's a lot you can learn just by this kind of sketching. Questions about that?
Why is the B field going?
Yeah. I have to make the drawing. I'm going to exaggerate the fall off of A here. Right, it's getting weaker. Okay, so I put a curl meter. Which way does it spin? It spins clockwise, which is right-hand rule into the board, into the page. Okay, now there's a really interesting thing you can do. So this was just a current wire, but let's suppose we took a cylinder. Let's take a cylinder like this. And I'm going to have current flowing in that cylinder uniformly around the outside like that. Now I could do that by taking a lot of wire, making a lot of wire loops, stacking them up, just just like the wire loop that we made, stack it up now on the cylinder. Or I could even have a coil, a helix. So I have one piece of wire that is wound in a helix. As long as the winding is tight, okay, not a real beautiful helix, but there's an example. That's called a solenoid. Now let's investigate the A field and the B field outside of the solenoid. Okay, so the A field is going to look a lot like what we just drew, right? We're not being very careful here about how things fall off, so it's going to qualitatively look the same. It's quantitatively not exactly the same. How things, the details of how things depend on distance is not exactly the same. So, but it's going to look a lot like that, except, and here's the interesting part, the B field inside here is uniform. The B field inside here is the same everywhere, same strength. B is uniform inside. But B is actually equal to 0 outside. There is no magnetic field outside the solenoid. Again, as long as you're far from the ends. The solenoid has to end, and you get fringing field coming out the ends. So we're talking about right in here, right in this region here. There's no magnetic field just outside of the solenoid, far from the ends. You get fringing fields outside of the solenoid of finite length. Of course, that's the only kind of solenoid you can make. So the fringing field. So we have to say, stay away from the ends. Get it close to the solenoid wall. There's no magnetic field outside, but there is an A field outside, and we've drawn that. And so you might ask, well, man, if there's an A field and it looks kind of like that, why isn't there a curl? Okay, and that's what we're going to investigate that. It's going to take, and you've encountered this before, and I've kind of let it go by. You've actually haven't drawn attention to it, but we've had situations like this. You have fields that look like they diverge, but the divergence is 0, and now we've got a field that looks like it curls, but the curl is 0, and that's where there's a little bit of, what's going on here? Okay, so I'll explain that to you right now. Okay, but before I give you the explanation, I just wanted to point out that the interesting thing. Whoa, what happened to my solenoid? Oh, I have a blank picture, a blank page, and there is my solenoid. Solenoid is a way of making a uniform magnetic field over some volume, but doing it in such a way that you don't have straight magnetic fields going on. So you can, you do fringing, but at least close to the solenoid. You can avoid, so you can make a magnetic field in this region, but not outside. That's very convenient to you. And the magnetic field inside the solenoid is the uniform. It's the same, points in the same direction, the same strength everywhere inside the solenoid. Very handy thing to be able to do. Now, for a capacitor, we were able to make an electric field that was uniform between a capacitor plate, and solenoid is a common way of making a magnetic field uniform over some region. So if you want to do experiments of something inside of a uniform magnetic field, this is really probably the easiest way to do it. Is just make a big enough solenoid that it encases the volume you want to do the experiment in. And you don't get a lot of magnetic fields, at least not right outside of the solenoid. Fringing fields, yeah, you got to deal with the fringing fields. Okay. Any questions about that so far? I'm going to go address this mystery. We have things that look like they should curl, but they don't. Things that look like they diverge, but they don't. So I'm going to talk about that. They're kind of special cases that we need to consider. But I'm going to give you time here. We've got this A field, the phi field, curls and divergences and gradients all over the place. It's just like a snowstorm of Dell operators. Are you dreaming Dell operators yet? Okay, so I want to address this question here, which we haven't really addressed before, and I want to start with the divergence. There are fields that look like they diverge, where the divergence is 0 in most places. Okay, and that's a funny thing, and I'll give you an example. Let's suppose we have a charge Q at this point, And you can write down the electric field. The electric field is just Q R over R cubed, right? If I put Q at the origin, that's the electric field. And I could write this in Cartesian form, XX hat plus Y hat plus Z hat over this mess, x squared plus y squared plus z squared to the 3 halves. Kind of messy, all right? If you plug that into your divergence machine, now, well, first to heighten the surprise here, let me first make a plot of this, right? We've plotted this before. It's like a hedgehog here with his quills pointing outward, and the arrows get smaller, like 1 over the square of the distance as you go away from this thing. All right, plug this into your divergence machine. Calculate, crank it out. It's a little bit of a mess. We'll do that tomorrow night. Anybody want to guess what the answer is?
0.
Yeah, it's 0. Ooh, what? It looks like it diverges. Why is it 0? It looks like it diverges, doesn't it? I mean, that field looks like it diverges, but it doesn't diverge. Except, okay, now there's a caveat. It's 0 everywhere except one place.
We're in the center.
At the origin. You can't take the divergence at the origin this way because the field is not defined at the origin, right? So the value of E is not defined at the origin, and the gradients of E are not a little hard to define because it's blowing up. Okay, so for x, y, z not equal to 0, that is not at the origin. Okay, but wait a minute, we have, remember this should follow Gauss's law, Maxwell's equation, Maxwell's first equation, 4 pi rho. The divergence of E should be 4 pi rho. What is rho? Rho is the charge density. What is the charge density somewhere not at the origin?
0.
0. There's no charge outside. There's only charge at the origin. So this should be 0 when you're not at the origin, right? Rho is 0 away from origin. And we've given it this kind of thing that you can only really do in mathematics in the sense of having a point-like thing. Right? There are no physical point-like bodies, but we could think of this point-like thing. And that's the reason why this is getting kind of strange, because we have this mathematical thing where it's 0 everywhere except at a point. And it can't be 0 at the point. That's very difficult to describe mathematically, but we do have mathematical ways of describing this, which you'll learn. And one simple way is called a Dirac delta function, which is not really a function per se, but it is an example of something. It's 0 everywhere except not at one point. And it's divergent at one point, in fact, because it represents a finite charge in an infinitesimal volume. And that's what rho represents here. Okay, so you should get 0. Okay, now let's go back. Remember Gauss's law. I'm sorry, excuse me. Boom, that was just Gauss's law. Gauss's theorem. I was trying to remember to make you sure you're not confused on that. Gauss's theorem. Let's write down Gauss's theorem for using the electric field. Do you remember the Gauss's theorem? Anybody?
Triple integral.
Good. Of the divergence of the volume. What does that equal?
Surface integral j dot dx.
Yeah, in this case I'm going to use E, right? That's true for any vector field J. Gauss's theorem holds for any vector field. I'm going to write it for the electric field. Okay. Now the left-hand side there, the divergence of E, if we put as this surface, now the volume is a sphere surrounding the point, right? This is a Gaussian surface. Put it as a sphere surrounding the point. But the divergence of E is 0 in most of that volume. But it can't be 0 everywhere, and I'll show you why. It can't be 0 everywhere. Right? We said this is 0 if we have the volume, which is a sphere surrounding the point with a charge. And so the right-hand side is not 0. So the left-hand side can't be 0. Even though it's 0 for most of the volume, it's not. The integral is not 0. The right-hand side is not zero. Let's look. You've done this. This is the Gauss's law exercise. Here's the electric field pointing outward. E dot dA is, E and dA are parallel to each other. And so the integral, right? This is the Gaussian surface thing. E dA, strength of the electric field is the same over the surface. We can factor it out. So this is just E times the area of the sphere. E times 4 pi r squared. It's not zero. And in fact, we know what E is. We wrote it down. There's E. E is Q over, in the direction, the magnitude of E is Q over r squared. So this is, E is Q over r squared. So E times 4 pi r squared is just 4 pi cubed. Excuse me a second. Didn't get it. Okay. So that integral on the right-hand side is just 4 pi cubed, right? That's Gauss's law, expressed in integral form. So the left-hand side can't be zero. It's zero most of the volume, but it's not zero at the origin. In fact, it's got just enough at the origin to make that integral not zero. Okay. Okay. So let's get sorted here. What in the world have we just discovered? There are fields that look, when you draw them, that look like they should diverge, but they're only diverging at a point. There's only one point here where this field diverges, and that's where the charge is. It doesn't diverge anywhere else. It thins out just in exactly the right way because there's no other charge. It's just thinning out. The only place where there's a divergence is at the origin. So the divergence is localized to the point. The divergence is only at the origin. It does diverge, but only at one place. So to take an analogy to that, if I had water flow on this table and I have a little source of water coming up here, the water would be flowing outward like this, and it's thinning out, but it's diverging only at where the source is. It's just flowing, spreading out, but that's not a divergence. The divergence has to come right there where the source is. The same thing if we had a hole in here and we had water flowing in. It's flowing in, but the divergence exists only where the hole is and it flows in. Okay. Same thing happens with that solenoid field. The A field doesn't have a curl the A field doesn't have a curl outside the magnetic field. Even though the A field is dropping off, diminishing, it's got a curl only inside the solenoid, not outside the solenoid. I'll give you another example here in terms of let's do the line charge. Remember we had a line charge of strength lambda, charge density lambda, and you found the electric field here in 2 dimensions is 2 lambda r times r hat. So the electric field is falling off like 1 over r from the line charge. And this is 2-dimensional now, so it's a little bit easier. If I take the divergence of this electric field, plug that into my divergence machine, what do you think I get? Zero. Yeah. So this is 2 lambda xx hat plus y hat over x squared plus y squared. Okay, you're going to do that in your homework. Right. You're going to do that in your homework. The divergence of that is 0. And you might think I've made a mistake here. It can't be 0, but it is 0. It's non-zero only at the origin. So this divergence is 0, not at origin. It has the divergence only at the origin. Okay, so if you sketch that field, it looks like it's diverging. And in fact, there is a divergence, but it's just not diverging everywhere. It only diverges at the point in the origin. Yes, sir. Mr. Luker.
Why is it just x squared plus y squared?
Yeah, this remember is a line, and I'm looking along the line. The line is along the z-axis, and the electric field doesn't depend on where you are along the line, and it points radially outward. So in the xy plane, that's what the electric field is like in the Cartesian coordinates. Okay. So it falls off like 1 over distance, and it's pointed radially outward. In a Cartesian form, that's what that would be.
Okay, I just thought you had the square root of it.
Ah, no. Okay, good. Thank you. So let's remember r hat can be written as r vector over r. So the electric field can be written as 2 lambda r vector over r squared.
Okay.
And there's the r vector, and there's the r squared. Okay? All right, good. Yeah, good that you're watching for that. Yes, sir, Mr. Dowd.
So if it doesn't have one, does that mean it must have the other at that point? Or
No, if it doesn't have one or the other, you mean curl?
yeah.
No. So this electric field has no curl anywhere. The curl of E is 0 everywhere, even at the origin. It just means that the divergence machine, where you take derivatives, only works where the function is not singular. That's the moral of the story. Using the Cartesian form of the divergence or the curl or the gradient only works if the function is not divergent. It doesn't. I'm using divergent in 2 different meanings there. If the function does not blow up, it's not singular. Okay. So, and you can see this function blows up at the origin. And so plugging that into the divergence machine works everywhere except at the origin. You just can't evaluate the divergence because the function is blowing up at the origin. So you have to find another means of evaluating the divergence other than plugging it into the Cartesian machine. Does that make sense? Okay, it's a thing to watch out for. It's a little bit surprising, but then when you see it